Hidden for weeks in the Milky Way's star crowd, 3I/ATLAS slipped past automated surveys. Then it shattered and exposed chemistry older than Earth. How did a tiny interstellar relic dodge detection, explode at perihelion, and spill CO2-rich, nickel-laced secrets? Using telescope logs, JWST spectra, and amateur archive finds, we'll show why this rewrites what we can and can't see. Let's dive right in. When astronomers finally spotted 3I/ATLAS on July 1st, 2025, they thought it was a routine discovery, another interstellar object rushing through the solar system. But the data didn't add up. The question wasn't how they found it, it was why they hadn't seen it earlier. For nearly a month, 3I/ATLAS drifted through the most crowded stretch of our sky, directly across the Milky Way's galactic center. Millions of background stars, dense nebular dust, and constant brightness fluctuations turned every frame into chaos. Automated telescopes like ATLAS and Zwicky were built to scan for moving dots in relatively clean skies. In the galactic center, subtraction algorithms collapsed under the weight of starlight. The result? The comet's faint motion was buried. Every time the algorithm tried to subtract the stars, it also erased the comet. It was there all along, glowing faintly, moving slowly, yet treated as an artifact. That single blind spot exposes something bigger. If one active interstellar object could hide there for almost a month, how many others have passed unnoticed through that same star-crowded fog? Weeks later, amateur astronomer Sam Din refused to accept the gap. He dove into public archives from May and June, aligning coordinates and frame timestamps. And what he found was stunning. In data from May 7th through June 25th, the object appeared exactly where orbital predictions later said it should be. NASA's TESS satellite had imaged it at 6.4 astronomical units, already faintly active. By June 21st, Chile's Vera Rubin Observatory recorded a developing coma over 13,000 kilometers across. The comet wasn't born in July. It had been active, growing brighter, shedding gas, all unseen. Sam's recovery of these lost frames wasn't just a technical fix. It was a message. In the age of automation, human curiosity still sees what algorithms ignore. When the first orbital calculations came in, they shattered expectations. 3I/ATLAS wasn't bound to our sun. It followed a hyperbolic path with an eccentricity over 6.14 and a velocity of 58 kilometers per second, nearly twice as fast as Borisov and far beyond Oumuamua. But the real clue was its trajectory. Unlike previous interstellar visitors that came from the galactic north, ATLAS approached from the south, the direction of the galactic center. Its motion through the Milky Way showed a steep inclination and a powerful vertical component, signatures of an origin in the galaxy's thick disk, a region filled with ancient, metal-poor stars. In plain terms, this wasn't a new traveler from a nearby system. It was a 9-billion-year-old relic, older than Earth, older than the Sun, carrying frozen chemistry from an era when our galaxy was still forming its first planets. Then came the spectra, the fingerprints of its composition. And that's where 3I/ATLAS broke every rule. The James Webb Space Telescope, observing on August 6th, revealed overwhelming emissions of carbon dioxide. The CO2 to H2O ratio, around 8.1, one of the highest ever measured in any comet. Later, after it fractured, that ratio climbed even higher, close to 15:1 in its exposed core. It wasn't just carbon dioxide. Webb and ground-based observatories found carbon monoxide, cyanides, carbonyl sulfide, and a strange emission of atomic nickel, but no iron. Normally, comets release nickel and iron together, forged side by side in early planetary dust. 3I/ATLAS defied that chemistry. Even stranger, the comet lacked common carbon chains, C2, C3, seen in every other known comet. Its light polarization pattern, how the dust scattered sunlight, was extreme, beyond any known object, hinting that its coma contained icy grains and dark organic filaments irradiated for billions of years. Each measurement screamed one message: this comet's chemistry doesn't belong to our solar system. Scientists split into two camps trying to explain the chemical chaos. Theory 1. The primordial Relic model. If 3I/ATLAS truly came from the thick disk, it formed in a star system with low metallicity, meaning fewer heavy elements, colder disks, and chemistry that froze CO2 first. Water stayed trapped deep inside, shielded by thick crusts. Theory 2. The buried core model. Billions of years of cosmic radiation might have built a hardened outer shell that kept water locked inside while letting CO2 escape first. The comet we saw before its breakup was only exhaling its outermost layer. The real story, the deeper composition, stayed hidden until it cracked. Both models fit the data. Both suggest an origin in a long-dead red dwarf system, now lost in the galactic crowd. Either way, it's not fantasy, it's chemistry, backed by telescope spectra, laboratory analogs, and galactic dynamics. And that's what makes it unsettlingly real. As Atlas neared the sun in late September, it disappeared from Earth's view, hidden behind the solar glare. But one world had a front-row seat: Mars. On October 3rd, the comet passed just 28 million kilometers from the red planet. Orbiters like ExoMars and Mars Express turned their sensors away from Mars itself and toward this interstellar intruder. What they saw overturned months of assumptions. The Trace Gas Orbiter detected nickel embedded in complex organic dust grains, not just atomic vapor. It also found traces of iron locked inside crystalline silicates, invisible to Earth-based spectroscopy. The comet hadn't lost its iron, it had simply hidden it inside heavier grains that never vaporized. In other words, the chemistry wasn't broken. It was layered. Ancient organics rich in nickel breaking down easily, while iron stayed sealed away. That discovery redefined how we interpret cometary deficiencies. Sometimes it's not missing, it's just hiding deeper than our instruments can see. When the comet reached its closest point to the Sun, 1.36 astronomical units on October 29th, the pressure became too much. Thermal stress and internal gas buildup tore it apart. When it re-emerged from behind the Sun in early November, telescopes went wild. 3I/ATLAS was 4 times brighter than expected. It wasn't a flare, it was a disintegration. The nucleus had split into 2 distinct fragments, now labeled 3I/ATLASA and 3I/ATLASB. That breakup was catastrophic and perfect for science. For the first time, instruments like JWST and Hubble captured fresh, untouched material, ice and organics that hadn't seen sunlight for 9 billion years. The interior ice was nearly pure CO2 with faint traces of water, sulfur compounds, and nickel-bearing organics. Most astonishingly, JWST detected polycyclic aromatic hydrocarbons, PAHs, complex carbon molecules, the same kind found in meteorites and prebiotic chemistry on Earth. But these PAHs weren't identical to ours. Their infrared spectra suggested they formed under colder, dimmer starlight from a small, ancient red dwarf. The conclusion hit hard. 3I/ATLAS likely formed around a dying red dwarf in the thick disk, a world that's long gone but whose chemistry still speaks across time. Hidden for weeks, misread by algorithms, and nearly missed entirely. 3I/ATLAS is a case study in our cosmic blind spots. Our surveys are optimized for convenience: clean skies, sparse star fields, repeatable subtraction. But the galaxy doesn't care about convenience. Objects from the southern galactic plane, the same direction ATLAS came from, are hardest to detect. Statistical models assume uniform sensitivity, but this single comet proved that's wrong. If one large interstellar object almost escaped notice, smaller, dimmer ones probably pass through every year, unseen. This isn't conspiracy. It's a design flaw, and scientists are already responding. The Vera Rubin Observatory has begun retraining its detection models with machine learning systems built to handle crowded stellar fields. Data from Atlas's missing month are now being used as the baseline training set. The next 3I/ATLAS won't get away so easily. Every breakup is bittersweet, but this one was gold for science. From the dust cloud, astronomers extracted the clearest picture yet of interstellar comet evolution. A small nucleus, under 1 kilometer across, a rotation period around 16 hours, CO2-dominated activity, beginning far from the Sun extreme age, between 7.6 and 14 billion years. A chemical fingerprint entirely unique: high CO2, low water, nickel-rich organics, and minimal carbon chains. 3I/ATLAS didn't just teach us about comets. It showed how much of our galaxy's early chemistry still exists, drifting quietly through the void, waiting to be found. After all the data, the light curves, the spectra, the orbital math, one realization stands out. 3I/ATLAS wasn't an alien spacecraft, nor a random rock. It was a chemical time capsule, a fragment of a world that formed when the Milky Way was young and chaotic. For billions of years, it wandered unseen, scarred by cosmic radiation, yet still intact. Then, for a few short months in 2025, it passed through our neighborhood, burned in sunlight, and broke apart, revealing a secret that had been frozen since before the Earth existed. That's not science fiction. That's the real, documented story of how the oldest comet we've ever studied almost slipped through our fingers, hidden in a sea of stars. If you made it this far, think about this. Every streak of light, every tiny anomaly in a telescope frame could be another messenger from the galaxy's past. How many of them are we missing? Right now? Tell me in the comments what you believe. Is 3I/ATLAS the first of many thick disk relics we'll find, or a once-in-a-lifetime encounter we were lucky enough not to lose? For billions of years, 3I/ATLAS drifted alone, silent, invisible, forgotten. Then, for a brief moment in 2025, it crossed our skies and tore itself apart, revealing chemistry older than Earth itself. What are the odds that we saw it at all? That a fragment of the galaxy's ancient past chose this century, this year, us, to witness its final breath? It's not just a comet. It's proof that our galaxy is still speaking, and we're only beginning to listen. Somewhere out there, another relic like Atlas is already on its way, hidden in the glare, waiting for someone to notice. So, what will we discover next time? Tell us what you think in the comments. Was Atlas a one-time miracle, or the start of a new era of interstellar exploration? If you love stories that turn data into discovery, make sure to like this video, subscribe to Galactic Breaking News, and turn on notifications so you don't miss the next cosmic visitor we uncover. Because the universe is still writing, and we're here to read it.